This is week 4, and we only have one chapter to cover this week. It's chapter 6. As you might guess, it's a pretty big one. In chapter 6, we take a conceptual turn because up to now we've been working with discrete probability distributions, which can be modeled by histograms. And now we're going to pivot to continuous probability distributions for the rest of the class. So let's review that difference between discrete and continuous. If you were in class and I pointed at you and picked on you and said, "Hey, you, what's the difference between discrete and a discrete and continuous variable?" I'm sure you'd feel on the spot. Would you be able to answer the question? Okay, think about it for a second. Difference between discrete and continuous. I think we talked about this in week 1. Discrete numbers are spaced apart. They have space between them on the number line. So the most common example of discrete numbers are whole numbers, 1, 2, 3, 4, and 5, because if you put a dot on the number line at 1, 2, 3, 4, and 5, you would have that empty space between them. And then you can draw the histogram rectangles to kind of sit over those empty spaces. But a continuous variable, like the amount of water in a tank, flows continuously from empty to full, and it basically ends up touching every single point on the number line in between, with no spaces in between. So you can kind of maybe think about it as continuous numbers touch each other. They're just an infinite number of points on the number line that touch each other from one end to the other. So when we make this transition from discrete distributions to continuous distributions, we get a different set of properties, and some of them are pretty strange. So I wanted to kind of go over these properties at the very beginning of the chapter. A lot of this material is not really in the book. It's just kind of an overview. But I think it's important to understand these concepts before we dive into problems and examples. So one of the strange new features of continuous distributions is that we will have no more histograms of rectangles. These will be replaced by the smooth curves that sit over top of them. So I want to remind you of this visual. We've seen something like this. It was over here, I believe. When we were talking about the binomial distribution last week, we have this histogram with rectangles on it. And remember what happened when we increased the number of rectangles? The more rectangles there were, the finer and smaller the rectangles became, and the more they started to approximate the smooth curve overlaying them. So if you can sort of imagine taking this process to its limit, and these rectangles, when a number is continuous, it wouldn't range from 0 to 100, or even 0 to 1,000. It would basically be infinite. You have an infinite number of points. And therefore, what we really end up with is an infinite number of rectangles that are infinitely small. Each rectangle really just becomes a line segment. But if you connected the tops of those line segments, you would just get this smooth curve, and that becomes the distribution. Another important visualization is one we looked at a week or two ago, which is the pile of sand model. So when we're looking at continuous curves, we're always going to be drawing them with some kind of a smooth curve on the top. And we should always remember that smooth curve is not just floating up in the air. It really is just the top of a pile of many, many fine grains of sand. Each one of those grains of sand represents a data point, one number in the data set. And at some regions in the pile, they're denser, they're stacked. There's more of them in this region, so they stack up higher. And at other points, they're not quite as dense and they stack up lower. And I'm sure you'll remember that we also discussed that if you pick any individual grain of sand in this data set, like let's just say we pick this one right here, we can measure it in 2 ways, by how large it is and how common it is, or basically where it stacks up against all the other grains of sand. So if you just drop straight down to the number line, you get this one-dimensional measurement on the x-axis. That gives you a measure of how large it is. And then to get a sense of how common it is or how relatively large or small, the percentile is given by the percentage of the grains of sand to its left. And last week we also introduced the p-value. Remember, a p-value is the percentage of grains of sand that are in the tail cut off by that value. So either way, we represent percentages or probabilities as areas on this pile of sand. Feature of continuous distributions is that the height of the curve now measures something called probability density. I can't really call it a probability anymore because it doesn't really represent the height of a rectangle. The probability density, or sometimes called probability density function, PDF, is usually uninformative. It won't really mean much to us. It's kind of beyond our intuition to understand what it is. So we will actually work with it in one example today. But for the most part, the height of a continuous curve is now essentially meaningless. And we really have to start getting accustomed to thinking in terms of areas instead of heights. Okay, and that brings us around to the next very strange new feature of continuous distributions. The probability of any single value is 0. What? What does that mean? It means if I select one, let's just say I'll select one man at random, and I measure his height. What is the probability that his height is exactly 5 feet 10 inches tall? Now, my height is approximately 5 feet 10 inches tall, but I don't know. I might be off by a couple millimeters or something. What would be the probability of getting a man whose height is exactly 5 feet 10 inches tall? Well, believe it or not, that probability would be 0. Now, you might ask, well, how could that possibly be? That means that being 5'10" is impossible. Well, kind of, sort of. Remember a concept we talked about last week. We said that sometimes when there are a lot of values, then the probability of selecting any one of them becomes smaller and smaller. That doesn't necessarily make it an exceptional value. It just means that it's one out of many. For example, if there are 50 numbers in a list, you basically have a 2% chance of picking any one. Now, what would happen if you increase that number 50 to 50 billion? Or 50 trillion, 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 trillion? You see what's happening here? The probability of selecting any one of those values would be 1 over 50 trillion, which is pretty much 0. And if we take it to the mathematical limit where there are an infinite number of points on the number line, that means that the probability of selecting any one of them is 1 out of infinity. And mathematically, that is 0. Or again, if you think about each number as being represented by a rectangle on the histogram, these rectangles are shrinking down, and eventually they're just becoming line segments. They have no area anymore. So mathematically, we're seeing some pretty weird things happen. So rather than thinking about terms of height or the probabilities of single values, what we're going to have to do instead is that proportions and probability can now only be measured by the area over an interval between a minimum and a maximum. And so I've brought along many examples so we can illustrate what's going on here. But I'll demonstrate with these visuals we have on the screen for now. So, for example, on this image, if we wanted to find the probability that a value is less than this one, we would need to take basically the area that's shaded in blue here. It's the area under the curve over an interval from 0 to 53 or whatever that is. And you can see the same thing on the pile of sand. If we wanted to find the percentage of grains of sand over here, we measure that as the area between 0 and this value. I'm going to go ahead and introduce you to a few continuous distributions that we're going to see in this course, And then after we take a peek at these, the next video clip will present these calculational examples. So there are some continuous distributions that are very common that we'll be seeing for the rest of this course. The first one is called uniform. That a uniform distribution means all values are equally likely, so its shape is just a horizontal flat line. And that distribution ranges from some minimum score on the left to some maximum score on the right. And I like this image because it actually used that term PDF, which means probability density function, to represent the vertical. And it actually gave us a value for it here, 1 over b minus a. And I like to use this uniform distribution as a teaching example, a pedagogical example, because we'll actually be able to use this number to work with it. The uniform distribution is the only one that's simple enough to actually calculate with according to this number. So it'll kind of allow us to see how it works before we go on to the curvy ones. Distributions in this course will be unimodal. That means that there's one mode or one peak somewhere along the curve. And those are very valuable for us to work with because they have tails. They taper off on both the left and the right, which means that they have significantly small values and significantly large values. And that's what we're going to be really concerned with. So there are a few of these that we're going to work with. The normal distribution, including its special case, the standard normal distribution, aka z-score distribution. And then there are a few others that we've never mentioned before. The student t distribution, the chi-square distribution, and the f distribution. Now, when we work with these for the next few weeks, the visuals are going to be very important. You're going to always want to draw regions of interest on these curves. So I've provided you with a template, and you can print as many copies of this as you want and need. So basically, here are several images of the standard normal distribution. Now, I'll take a closer look at that one too, just for a second on the screen. The standard normal distribution is a bell curve. And when it's standard, that means that it's measuring z-scores down here. 0 in the middle with a standard deviation of 1. And again, I like this image because it actually reminds us that the vertical axis is now probability density. This first page of the handout provides you with many miniaturized versions of that standard normal distribution, and we'll soon see how to use these as visual aids. The next page presents us with generic bell curves with the x-axis not labeled, and we might use these for normal curves or t-scores. Then there are a couple of right-skewed distributions that will come towards the end of class, called the chi-squared or f distributions. They both basically look like this. And here's the uniform. All right, let's go through some examples now to visualize how we can use these smooth curves to work with probabilities and percentages.